In this video, we will talk about the null hypothesis. The null hypothesis is the hypothesis that our variables are not related. In other words, the null hypothesis is the hypothesis that there is no effect, or that the effect is equal to zero. The index of our effect, whatever it is equal to zero. This sounds very strange. Why on earth would we make this hypothesis? Indeed, the null hypothesis is not intuitive at all. It's maybe the strangest thing about statistics. And that's why we need to pay extra attention to understand why and how it is used. Let us begin with a simple example, one that you are already familiar with. The one where you tried an intervention with 20 children, and you note that 13 of them show improvement. And then you wonder if the intervention is worth using further. Should you spend more time to develop it? Should you apply it to more children? On the face of it, 13 improved versus 7 non-improved sounds quite encouraging. How can we evaluate whether it is worth the effort? Let's state the null hypothesis. This is the unintuitive step. Imagine that the intervention does not work. What would happen if the intervention did not work? Well, you would still expect changes in performance because people don't get exactly the same score if tested twice. So the changes can be just random noise. Some scores will go a bit up, some will go a bit down, some won't change, and that's just randomness. That's what the null hypothesis amounts to, that any differences observed are due to random noise, are due to sampling. But this allows us to answer a specific, very useful question. The question is, how likely is it really to get 13 versus 7 or more extreme just by random variation? If there were a random process that produced two outcomes and you ran it 20 times, how likely would you be to get the same outcome 13 or more times? Well, now we are quite familiar with one random process of this sort that can help us evaluate the expectedness or unexpectedness of this outcome. And this random process is the coin flip. This is exactly what we need. Imagine flipping a coin 20 times. We can calculate exactly how likely it is to get 13 or more heads out of 20 coin flips. There is only one way you can get all heads in 20 tosses, and there are 20 ways to get 19 heads and 190 ways to get 18 heads, and so on. You may be wondering where these numbers come from, and the answer is I asked the computer to produce them using the appropriate formulas. If you want to count them, you would have to list all million plus different patterns that are produced by 20 coin flips. Don't do that. The computers do that for us, and the answer turns out to be about 13%. So the probability of getting 13 or more heads by flipping a coin 20 times is about 13%. Is that impressive? Is that unexpected? Would you be surprised if someone got heads 13 times in 20 coin flips? Clearly not, if this can happen 13% of the time. So 13 out of 20 is not unexpected to happen entirely by chance. And there's nothing more random than a coin flip. So this is not an unexpected outcome. Going back to our example then, 13 versus 7 doesn't sound so impressive anymore. In other words, 13 out of 20 is not an unexpected outcome if we assume that there is no effect, just random sampling. In other words, if we assume the null hypothesis. We just found out that assuming the null hypothesis leads to an expectation of a result like the one we got, with the probability of 13%. This is not a very low probability, and so we cannot reject the null hypothesis. What does this mean? It means we cannot dismiss the possibility that our outcome with the children was simply due to random noise and not due to an effect of the intervention. This doesn't mean that we know it wasn't the effect of intervention. It doesn't mean we know anything about the cause of our finding. It just says that because it's not unexpected, if we assume just random sampling, we cannot dismiss the possibility that random sampling was also at work in our study. So it remains a possibility. This null hypothesis cannot be rejected. Why do we need to do all this? It sounds very strange. What we really want to know is something about our hypothesis. Our research hypothesis is that the variables are related. Our research hypothesis in this case is that the intervention works, or at least that's our research question. We want to know the probability that our intervention works, and we want to evaluate this probability based on the data we got. This is what we would like, the probability of our hypothesis being true given the data. This is what this notation means. The probability of our hypothesis given the data that we have. Unfortunately, this is not possible. You cannot calculate this probability because it depends on other things which are unknown. So forget about calculating this probability. It's just not possible. That's why people have resorted to something that's possible and to some extent useful. What is possible is to calculate the probability of a data pattern based on an assumption of a specific well-defined hypothesis, such as the null hypothesis. So the probability of a data pattern given the null hypothesis. This is something we can calculate because all we need is the sampling distribution from the null hypothesis. If we have the sampling distribution, then we can evaluate any probability we want. Let us consider another version of the same example. This time, we will take into account the actual test scores. So you have obviously tested the children before and after the intervention. And you have calculated different scores or change scores as they're known, and that's the difference in the score on the same test before and after the intervention. So you subtract each child's score before the intervention from the same child's score after the intervention, and you get a difference which tells you how many points this child's score changed between before and after the intervention. And let's say these are the results. So the first child improved by 1 point, the second child improved by 2 points, a fourth child did not change their score, one child went down by 2 points, and so on. If you count, you will see that 13 of these are positive, and these are the children that we suppose improved, even if by only 1 point. The first thing we want to do is to state a null hypothesis. The null hypothesis is that there is no effect of the intervention. No effect means that the expected difference score or change score is 0. No change means that there would be no difference between the score before and after the intervention. This is what the null hypothesis states. So now we have to evaluate the scores that we got in light of the null hypothesis. First of all, we calculate the mean change score, which is 0.85. The mean of these numbers is 0.85. Okay, that's our mean. The standard deviation of these scores is 1.14, and the standard error of the mean is evaluated by dividing the standard deviation by the square root of the sample size, and that's 0.25. If we divide the mean by its standard error, we see that the mean is 3.4 standard errors away from zero. The mean is 3.4 standard errors away from zero. This is our finding. What is the probability that we would obtain a mean 3.4 standard errors or farther away from zero? Because zero is what the null hypothesis predicts we should have gotten. That would be the population mean under the null hypothesis. Instead, we got 0.85, which happens to be 3.4 standard errors away. So how likely is it to get a mean in a sample that is 3.4 standard errors away? If we look this up using the t-distribution for a value of 3.4 with 19 degrees of freedom, because sample size is 20, we find out that the probability is 3 in 1,000, 0.3%. So this is our result. Let's recap and see what it means. The null hypothesis was that the mean difference score is 0. That is the hypothesized population mean. Are we drawing our sample from this population where intervention has zero effect? The alternative hypothesis, this is called H1 or alternative hypothesis. This is the one we actually care about and is the opposite of the null hypothesis. So our hypothesis, or our research question if you prefer, is that the mean difference score is not 0, that there is some effect of the intervention, that it's not 0. Like I said, we cannot evaluate anything about this, but we can evaluate something about this one. We actually got a mean difference score of 0.85 with a standard error of 0.25. This is 3.4 standard errors away from the hypothesized mean. And so we asked, how likely is it to get a sample mean that is 3.4 standard errors away? Pretty much everything is possible by sampling. You can get unlucky and have a sample mean that is quite far away from the population mean, especially with small samples. We should be very clear about that by now. But how likely is it exactly? The answer for this one was 0.003. This is the probability of getting a sample with a mean that is 3.4 standard errors away from the population mean. So this is a very unexpected outcome. Based on what the null hypothesis suggests, if the null hypothesis is true and the population mean is 0, the value we get from our data is very unexpected. This means we can reject the null hypothesis. It doesn't mean we are completely sure that the intervention has produced this effect, but it does mean that it is very unlikely for random sampling to have produced an effect of this size. This allows us to reject the null hypothesis for this test. Actually, let me open a parenthesis here and say that from a methods point of view, this is not something we would ever do, because people improve their scores just by taking a test twice. So this would be a very stupid thing to do if you were actually running a study. But from a statistics point of view, we're just looking at the difference scores. So this is the statistics part of this course, not the methods part. And we're just dealing with evaluating this change as to whether it can be drawn from a population with a mean of 0 or not. Close parenthesis. An alternative approach to perform this kind of analysis is to think about interval estimates. So if we go back to our two hypotheses, the null hypothesis that the mean difference score is 0, and the alternative that it isn't 0, we have our sample mean and standard error. What we can do with these is we can calculate the margin of error. Let's say we go very conservative and decide to calculate a margin of error for 99% probability. So we look up the critical value of the t-distribution for 0.99 probability with 19 degrees of freedom, and we multiply this critical value with our standard error. The critical value is 2.86, the standard error is 0.25, so the margin of error is 0.72. The 99% margin of error is 0.72, around our observed mean of 0.85. We can now calculate the 99% confidence interval by subtracting and adding this margin of error from and to the mean. So the 99% confidence interval is from the mean minus the margin of error to the mean plus the margin of error. So this is our 99% confidence interval from 0.13 to 1.57. This 99% confidence interval does not include 0. It starts with a positive number and ends with a positive number. It's all to the right of 0. Our 99% confidence interval for the mean is well above 0 and includes values of effects for the 99% confidence that are all positive. 0 is the predicted mean from the null hypothesis, and it is excluded by the confidence interval we calculated. This means that the probability of a finding like this is the finding now, the probability of this finding is less than 1% if the null hypothesis is true. Why 1%? Because this is the 99% confidence interval and 0 is outside of it. So again, we conclude that this is an unexpected finding under the assumption of the null hypothesis, and this allows us to reject the null hypothesis. This procedure is equivalent to the one below. The difference is that instead of reporting a p-value, we report a confidence interval and check whether 0 is included in it. Otherwise, the two procedures are exactly the same. The previous procedure with the p-value is the one most commonly seen in the literature. This one with the confidence interval may be easier to interpret properly and is now gaining acceptance in the literature very slowly. You can use either one of them. Summing up, the null hypothesis states that there is no effect, no relationship. The effect is equal to 0, the index of the effect is equal to 0, our statistic is equal to 0. Something is 0. Then we calculate the observed index, the observed effect or index of relationship from the data, whatever it is that can be evaluated as an index of our research question. Then we evaluate the unexpectedness of such an effect if the null hypothesis is true. In other words, we are evaluating how likely it would be to get an effect of this size or greater by sampling from the null hypothesis. This evaluation is based on the sampling distribution of the index we have calculated. If the effect is unlikely based on the null hypothesis, then we reject the null hypothesis. If the effect is not unlikely, it's not too unexpected, then we cannot reject the null hypothesis. We never accept the null hypothesis. All we can say is that we cannot reject it if the effect is not too unexpected. This probability that we calculate based on the null hypothesis is called the p-value, and is the probability of obtaining an effect that is large or greater than the one we observed if the null hypothesis is true. This is the crucial idea, and the one that is actually quite difficult to wrap one's head around. It's based on the variability of random sampling and then sampling distributions. So it's very important to keep in mind that when you have a population and draw samples from it, it is possible, although not likely, that you will get samples which are very unrepresentative. Sometimes you will get unlucky and draw a sample which will have a mean that is very different, that is far away from the population mean. This can happen, and it happens more often if the sample size is small. That's the crucial idea that we're taking advantage of in getting this p-value on the basis of the assumption of the null hypothesis. The most important property of the p-value that you need to keep in mind is that the p-value is conditioned on the null hypothesis being true. What does this mean? It means that the p-value is interpretable only as a consequence of the null hypothesis being true. The p-value means nothing about any other hypothesis or about data. So, for example, the p-value is not the probability of your data. Your data are already collected. They have a perfect 1 probability. They're just there. It's not a probability of your hypothesis because that's unrelated to how the p-value is calculated. It's not the probability of the null hypothesis because you assume the null hypothesis is true before you can begin to calculate the p-value. So if you have a p-value, this means that the null hypothesis is assumed true. It is also not how certain you can be that your data aren't due to chance. This is a misunderstanding we see very often, and sometimes we see it even in statistics books, which try to become more understandable by being horribly inaccurate. This is not a good idea at all. The p-value is not about your data or about what caused your data. This is not possible to evaluate in any way. This is why I use the coin flip example first, so that you have it very clear in your mind that where we get the p-value from is a simulation that happens later and independently from your data. We simulated a coin flip after our study to see how frequently we would get an outcome like the one in the study. This says nothing about the data you obtained in the study. It only says how likely it is to get a similar outcome by a random process. So it will serve you well to keep the coin flip example in your head every time you have to interpret a p-value. And finally, a few words about the criterion. When is something expected or unexpected? We need a kind of threshold to decide when something is too unexpected so that we can reject the null hypothesis. How low can the p-value be before we can state that the obtained effect is too unlikely to have arisen by random sampling from the null hypothesis? The criterion used most frequently for this decision is the 5% criterion. So if the p-value is less than 0.05, then we reject the null hypothesis. If the p-value is greater than or equal to 0.05, then we don't reject the null hypothesis. Perhaps we can say we retain it. We cannot say we accept it. The null hypothesis can never be accepted because the effect can be smaller than what our standard error can detect. So we can never have any confidence in accepting the null hypothesis using this kind of statistics. The 5% criterion is arbitrary, and in fact many say that it is too loose, too relaxed, and we need more stringent criteria for rejecting the null hypothesis because this may lead to many false findings in the literature. Still, it's the one most often used. So you should interpret with caution any findings that rely on this arbitrary criterion, and you are free to use more stringent criteria in your own studies. What you should always remember is that there is no absolute law about this, and that it is just a convention that people have come to in the literature. Different literatures may have come to different conventions.